Assalamualaikum. Let's learn about Chapter 7, Electromagnetic Induction, or in Malay, Aruhan Electromagnet. So previously in Chapter 6, we have learned that current will produce magnetic field around it. But in this chapter, we are going to reverse the process where from the magnetic field, it can produce current. That's why we call it as electromagnetic induction, and the process will produce current in the wire. Electromagnetic induction is the production of electric potential difference or voltage or EMF or electric current across a conductor that's situated in a changing magnetic flux. So the main keyword is the changing of magnetic flux. What happens if the magnetic flux change? It will produce induced EMF or induced current. So we are going to look at the experiment by Michael Faraday. Let's say we have a solenoid, a bar magnet, and a galvanometer as shown in this figure. At first, there is no current in the solenoid. Why? Because the bar magnet is stationary, velocity is equal to 0, or there is no movement either inside or outside of the solenoid. There we can see the galvanometer not showing any deflection. Thus, there will be no current induced in the solenoid. The function of the galvanometer is to detect the presence of current in the solenoid. Next, we try to move the bar magnets towards the coil, or we move it into the solenoid, masukkan ke dalam solenoid. What happen is, the galvanometer will show deflection, menandakan there is induced current in it. When there is induced current produced in the solenoid, there will be also induced EMF exist. Then we try to move away the bar magnet from the coil, ataupun daripada dalam magnet bar tu kat dalam solenoid, kita bawa dia keluar daripada solenoid. What will happen is the galvanometer will show deflection to opposite direction compared to the yang tadi kita masukkan, dia tunjukkan arah ke kanan, tapi kalau kita keluarkan dia tunjuk arah ke kiri. So arah induced current is also important. We are going to learn how to determine the direction of induced current later. Then, what if we change the pole of the bar magnet? Tadi kita masukkan north pole. What if kita tukar position, kita masukkan south pole pula? So, what will happen? There will also induce current in the solenoid. From this experiment, Faraday concludes that there will be a current induced or current is set up in a circuit as long as there is relative motion between bar magnet and also solenoid. So, mesti ada melibatkan pergerakan. Second one, current or EMF will be induced in the circuit when magnetic flux through the circuit change with time. So, bila bar magnet tu bergerak masuk ataupun keluar daripada solenoid, akan ada perubahan magnetic flux. Kita masukkan bar magnet dalam solenoid bermaksud magnetic flux akan meningkat. You need to understand what does it mean by magnetic flux. The number of magnetic field lines that can passes through the plane of loop. Kalau magnet tu dimasukkan ke dalam, semakin lama semakin banyak number of magnetic field lines daripada bar magnet can passes through the plane of loop. So, magnetic flux increase. Tapi kalau kita bawa keluar daripada dalam solenoid, kita bawa keluar bar magnet, so semakin berkurang magnetic flux in it. So, mesti melibatkan perubahan magnetic flux. If the magnet is situated outside of the coil, ataupun dia berada dekat dalam coil tetapi tidak bergerak, magnetic flux ada tetapi tidak melibatkan perubahan. There is no changes in magnetic flux. There will be no induced current in it. Another thing that Faraday found is when the bar magnet is moved at higher speed, the deflection on the galvanometer will increase. It shows that the magnitude of induced EMF produced in the solenoid will increase too. So, velocity of the bar magnet is proportional to the induced EMF in the solenoid. Semakin laju kita bawa masuk magnet tersebut, semakin meningkat nilai current dan juga EMF induced dalam solenoid tersebut. From the conclusion, Faraday comes up with an equation which is EMF equal to negative N times with the change of magnetic flux in time interval. So, negative shows the polarity of induced EMF or the direction of induced current with respect to the change in magnetic flux. This negative sign refers to Lenz's law. So, it related to the direction of induced current. We are going to apply Lenz's law when we want to determine the direction of induced current in the solenoid. N is the number of turns and times with the change of magnetic flux with time interval. So, to find the change of magnetic flux, we are going to use equation magnetic flux equal to BA cos theta. By definition, the EMF induced in a circuit will equal to the rate of change of magnetic flux through the circuit. We are going to apply Lenz's law when we want to determine the direction of induced current. By definition, Lenz's law is the direction of induced current always in the direction that oppose the original change in magnetic flux. So, dia mesti melibatkan perubahan magnetic flux. From there, we will determine the direction of induced current in the solenoid. Okay, ataupun we can also say that Lenz's law is about polarity of induced EMF yang dihasilkan di mana the magnetic field inside the solenoid will oppose the original change in magnetic flux through the coil. It is almost the same thing. Okay, it will help us to determine the direction of induced current. But first, we need to identify what are the causes or changes that produce the induced current. Then we are going to use right hand rule. How to use the right hand rule? Okay, what you need to do is you need to grip the solenoid. Okay, genggam solenoid tersebut. Gunakan you punya tangan kanan. And your thumb will follow the direction of north. Okay, and then the rest of your fingers will show the direction of induced current in the solenoid. Okay, what about the north and south pole dekat solenoid? It is from the direction of magnetic field inside the solenoid. Okay, contohnya macam gambar rajah ni. Bermaksud kenapa yang ni north, kenapa yang ni south. Arah magnetic field lines dalam solenoid ni, arah dia macam ni. Sebab itulah yang ni akan jadi north pole, yang ni akan jadi south pole. Then use your right hand grip rule to determine the direction of induced current. Okay, later I will show you how to determine the direction of magnetic field inside the solenoid. So based on this diagram, we can relate it with the bar magnet. So bar magnet itself, dalam bar magnet itu sebenarnya ada juga magnetic field lines which is directed like this. Okay, so dia keluar daripada north pole and then masuk melalui south pole. So dia seolah sama macam dalam solenoid ada magnetic field lines. So dia akan move from north to south. So now let's look at the example how to determine the direction of magnetic field inside the solenoid. Macam mana boleh wujud magnetic field dalam solenoid? It comes from the current induced in the solenoid. Okay, bila ada current induced in solenoid, the current itself will produce a magnetic field around it, and then kita akan tengok arah magnetic field dalam solenoid tersebut. So bila kita tahu arah magnetic field dalam solenoid, we can determine the north and south pole. After that, we can use our right hand rule to determine the direction of current induced. Okay, for the first example, we have a bar magnet which is directed to the left or move towards the coil. Kita nak masukkan dia ke dalam solenoid. And then, what will happen when we move this bar magnet into the solenoid? Semakin banyak magnetic field lines daripada bar magnet that can passes through the plane of solenoid. So, magnetic flux will increase. Bila magnetic flux increase, Faraday said that when there is a changing in magnetic flux, so there will be EMF and current induced. Lenz pula, dia cakap, to determine the direction of induced current, we need to oppose the change of magnetic flux. So, apa yang berlaku terhadap magnetic flux tadi? Magnetic flux increase. So, we need to oppose the change. Kita kena decreasekan balik magnetic flux dengan cara the direction of magnetic field inside the solenoid will opposite with direction of magnetic field from the end of bar magnet. Okay, so what we need to do is, first you kena tengok arah magnetic field on the end of this bar magnet. Yang masuk adalah north pole. So north pole arah magnetic field dia macam ni. Okay, so dia daripada north pergi kepada south. Okay, so kita ambil yang bahagian hujung ni lah, yang masuk dalam plane of this coil. Then, kalau lens kata kita kena oppose the change, kita nak kurangkan balik magnetic flux. So, direction of magnetic field inside the solenoid will opposite ataupun bertentangan dengan arah magnetic field daripada bar magnet. So, dia akan oppositely direction. Macam ni. Okay, so now you can determine the direction of north and south pole. So this end of the solenoid will be north pole and this one will be south pole. Sebab seolah-olah macam magnetic field dalam bar magnet ni dia pusinglah daripada north ke south pole. Okay, then use your right hand grip rule. Grip this solenoid using your right hand. Follow the direction of north pole using your thumb. And then the rest of your finger will show the direction of induced current. So arah induced current ke bawah. So, it will be like this. Ni cara kita nak tentukan arah induced current by using Lenz's law. This diagram shows the same thing that I have explained before this. So, when we move the magnet bar into the solenoid, the magnetic flux will increase. Then, Lenz said we need to oppose the change. We need to decrease back the magnetic flux with the direction of magnetic field inside the solenoid will opposite direction with direction of magnetic field from the magnet bar. So here you can see the direction of magnetic field from the solenoid is into this direction, while the magnetic field from the magnet bar is in this direction. So they are opposite direction. Okay, so when we have determined the direction of magnetic field in the solenoid, we can label which one is the north and south pole. Then use your right hand rule to determine the direction of induced current. Okay, another example. We move away the bar magnet from the coil ataupun kita pull it out daripada dalam solenoid, kita tarik dia bawa keluar. So what will happen if we pull away the magnet from the solenoid? The magnetic flux will decrease. Semakin berkurang number of magnetic field lines that can passes through the plane of solenoid. So Faraday kata, if there is a change in magnetic flux, there will be induced current and also induced EMF. So we can find the value by using Faraday's law equation and also Ohm's law. Meanwhile, to determine the direction of induced current, Lenz said that we need to oppose the change. Change of what? Change of magnetic flux. If the magnetic flux is decreased, we need to increase back the magnetic flux. So how to increase back the magnetic flux? Direction of magnetic field inside the solenoid is same with direction of magnetic field from the bar magnet. So first you need to determine the direction of magnetic field on the bar magnet, which is if we have this north pole, the direction of magnetic field on this north pole is like this. And then the magnetic field produced in the solenoid will be same direction with the magnetic field from the bar magnet. So it will be like this. Then we can label which one is north and south pole. Here we have north pole on the left side while south pole on the right side. Then we can use our right hand grip rule, okay, to determine the direction of induced current in the solenoid. So your thumb is direction of North Pole, and then the rest of your fingers will show the direction of induced current in the solenoid like this. Okay, this is another diagram to show the direction of magnetic field. Inside the solenoid, it has same direction with the magnetic field from the magnet bar because we want to increase back the magnetic flux.